Hello everyone, welcome back to this course on reinforced concrete design. We are in the third week of this series of lectures and this is our second lecture. The main aim of this week's discussion is the slab design. In the last class, we actually covered the remaining topic of beam design, which was bond strength and the development length, right? So with that, actually completed the beam design. And in case of slab design, you'll see we'll use the concept of beam design for this, the design of slab. Now, before we start discussing the design of slab, let us quickly revisit what is the definition of slab and what are the different types of slab that we are going to discuss in this course. Now, before we go into the definition of the slab, let us first quickly focus on the structural details. Say we have a room, as you can see here, a room is supported at 4 corners. So these are the columns at the corner. It supports a series of edge beam at the top, and then here we have the roof. Now on this roof, we apply certain load downward. For example, even the dead load of the structure is actually acting downward. So this roof is what we call a slab. So first thing to be noted here, if I draw the thickness of this slab here compared to the other dimension, so this dimension or the thickness is very small as compared to say Lx and Ly. So slab is a structural member for which one dimension is very small compared to other two dimensions, right? And if you look at this type of loading, obviously we do not have here any in-plane loading. So the loading applied to this slab offers a bending behavior of the slab, right? So the primary response to the loading of slab is bending, right? Now we can further classify slab into different categories, and these classifications can be done based on different features. The first one is obviously the shape of the structure. So we can have rectangular slab, triangular slab, circular slab, or for that matter, any other shape. Now in this course, we will not discuss other types. We will fully focus on different types of rectangular slabs and their design. Now based on the type of construction, we can again further classify slabs into different categories. As you can see, we can have solid slab, we can have flat slab. Then there are other types of slabs, they are also available. But in this course again, we will fully focus on these two types. This week we will talk about the design of solid slabs. We will have another week dedicated to the design of flat slab. Now beyond that, the bending behavior of the slab, depending upon the dominant direction of bending, we can further classify the slabs into two categories. The first one is the one-way slab. Another one is what we call two-way slab. Now, as the name suggests, one-way slab has significant bending in a particular direction as compared to the other direction, and hence it is called one-way slab. So from that definition, we can sense for two-way slab, we will have bending in two orthogonal directions. So once we get the geometry of the slab, then based on that and the support conditions also, we can decide whether it is a one-way slab or a two-way slab, depending upon the dominant direction of bending. For that, let us consider this example. As you can see here, the first example here is a rectangular slab whose dimension is meter is given. So we have 6 meter by 4 meter as the dimension. Now for this problem, we have supports at the two edges along the longer direction. So we have Ly as 6 meter and Lx is 4 meter. Now, if we apply a loading which is perpendicular to the plane, then obviously we will have deformation what is shown here, with the maximum deformation at the middle which is shown as delta max. Now, at the two extreme edge, the deflection is 0, so we will have no deflection there and maximum at the middle. Now, if we consider say different points along this line, and then if we plot the displacement, obviously all the points along this line will have this delta max, that is the central deflection from the other direction, as you can see here. So all these points will have the same amount of deflection, which is delta max. That means for this slab, the load that we apply is transferred to these two edge beams, and if you look at the direction of load transfer, it is predominantly in a particular direction. So if this is the situation, we call it a one-way slab. Now, if you look at the ratio of this Ly and Lx, so we have 6 by 4, which is 1.5. which is less than 2. Now, the point to be noted here is this ratio of Ly and Lx, it is less than 2, yet because of the support conditions, we have one-way behavior because we have deformation or deflection predominantly in along the shorter direction, right? So, a rectangular slab supported from opposite edge is always a one-way slab irrespective of the slab dimension, as you can see in this problem. Now, we have a second example where we have a 10 meter by 3 meter slab, but in this case we have supports along all the edges. Now, for this slab, if we again draw the deformed shape, we have along this shorter direction, we have delta max at the middle, which is 0 at the two edges. Now, if we consider, say, any point along this line, and then we plot it, obviously at this two extreme points, we have 0 deformation. Now, as we move inside, after a certain point, we will have this delta max, and this from this delta max, it will ultimately go to 0. So, for this problem, the aspect ratio is 10 by 3, which is more than 2. Now, if you look at the bending behavior, again you can see here, it has bending behavior predominantly in one direction. So, a rectangular slab supported from all 4 sides is considered as one-way slab even if the aspect ratio is more than 2, because the type of load distribution we have, which shows the bending is predominantly in one direction. So, first thing to be noted here, what is the aspect ratio for a slab? It is the ratio of the longer effective span to the shorter effective span. Now, just note that we define Ly as the longer span, so y direction having the larger span, x direction is having the shorter span. Now, in IS 456, we have dedicated clause for effective span length, because it is not only the span length, we have to find out the effective span length, and then we have to take the ratio to find out what is the aspect ratio for a particular case. Now, when we define this aspect ratio, it is valid only for rectangular slab supported from all 4 sides, right? So, let us see if we have this situation. So, here we have a 5 meter by 4 meter slab. Now, for this, what is the aspect ratio? It is by 5 by 4, which is 1.25, and it is less than 2. Now, for this case, if we draw the deformed shape, we get this type of behavior. So along the shorter direction, we have delta max at the middle. And obviously, because these two dimensions are comparable, obviously along the longer direction also, if we plot, we will have 0 at the two extreme. And then we have delta max at the middle. So for this problem, we have both these orthogonal directions, they are participating in the bending. So if the aspect ratio is less than or equal to 2, a rectangular slab is supported from all four sides, then we call it a two-way slab because of the bending behavior, which is comparable in two orthogonal directions, Ly, which are represented by Ly and Lx. Now, for this slab design, in case of beam, you have noticed we have, say this is the rectangular section, and we have, these are the rebars. So this is what we call clear cover. In case of slab also, we need to provide clear cover. We need to provide this reinforcement along the tension zone, and obviously we have concrete to take care of compressions. And for this design of this slab, what we'll do, we'll consider 1 meter wide strip, and then if we see the cross section here, so we'll have a rectangular cross section where the width is 1 meter. So this side is 1 meter, and then we will actually provide rebars at the bottom, and we'll design this as a beam section. Now, obviously, we have to provide steel along this direction and steel along this direction. So there will be steel along this direction also. We'll go into the details of that, but for the clear cover, the code recommends IS 456 clause 26.4.2 recommends nominal cover, and that is minimum 20 millimeter, which can be reduced to 15 millimeter for mild exposure and bar diameter 12 meter or less. So if we have a exposure conditions which is mild, and if the bar diameter is 12 or less, then we can provide minimum of 15, or otherwise we have to provide 20 millimeter nominal cover. Okay. And reinforcement also should satisfy this. The diameter, that is 5, should not be greater than d by 8, right? And clause 26.5.2 also provides a requirement for minimum reinforcement, which is 0.15% of the gross area for mild steel and 0.12% of gross area for HYSD bars. Now, this minimum value is for both the directions. As I explained here, in case of slab, we have to provide steel along shorter as well as along longer direction. So, for both these directions, we have to find out the minimum amount of steel depending upon the grade of steel that we are going to use. So, that we have to keep in mind. And obviously, in this process also, we have to take care of shrinkage and temperature effects. So when these will come, we'll explain what are their meaning. Now, as I have already explained that we need to provide rebars along two directions in case of a slab, there is a dedicated codal provisions for minimum spacing. So for example, if we consider, say, rebars along the shorter direction, so that means these are the rebars, then this distance is the spacing between the rebars along this direction. Now, maximum spacing allowed for this reverse, the main reverse, should not be more than 3D or 300 millimeter, whichever is less. So that is for the main reverse, which is shown here. For the secondary distributions, so we have reverse in the other direction. For example, we have reverse along this direction. So for these reinforcement also, we have the Codal provisions for maximum spacing, which should not be more than 5D or 300 millimeter, whichever is less. And the clause is 26.3.3. Why it is mentioned? Because if we have this maximum spacing more than these limits, then there is a chance of cracking, and the pattern of cracking can be different depending upon the spacing and the orientation of the reinforcement, as you can see here. Now, the main bars are always provided at the bottommost layer for obvious reasons. So, if we have, say, a 1 meter strip, so the main bars must be provided at the bottom, so that that main bar will get maximum D, or in other words, it will provide maximum lever arm in the dominant direction. So as you can see, we have main reinforcement here and we have secondary reinforcement. And if we place this following these guidelines for maximum spacing, we can control this random cracking. And for this also, for this type of orientations, again, the cracks may appear along the directions you can see, but that must be controlled by the distance between the two bar, as you can see here. So we will see as we progress further how to decide the spacing of these bars along the dominant direction and obviously along the secondary direction. So what we have learned here, that there is a condition of nominal cover depending upon the type of steel. Then the second thing is we have to provide main reinforcement in the bottom layer. For the design, we'll consider a 1 meter strip and we'll design it as a beam that we have already learned in our previous week lecture. And then we have some minimum reinforcement requirement. Then the diameter of the reinforcement is also restricted here, and obviously the maximum spacing of both main bar and the secondary reinforcement, right? Now, obviously if we have a larger span, we have more deflection at the center. So when we design a slab, we have to satisfy this deflection criteria. So for this deflection control, we have a dedicated clause which is 24.1. What it says: if rectangular 2A slab is supported from all four sides with shorter span up to 3.5 meter and loading up to 3 kilonewton per meter square, then L effective by D, that ratio, should be less than the values given below. So as you can see here, we have two different support conditions, simply supported and continuous. For that, different grades of steels are here, either Fe250 or 415. For that, the value of L effective by D should be less than this value. So if we have a simply supported case where we use Fe250, then L effective by D should be less than 35. So from this, we get the first idea of the total depth of the slab. So from the dimension, we can find out L effective, that we'll see as we solve one example. Then the first idea we get is this D should be greater than L effective by 35. And obviously for Fe415, this limit is L effective by 28. And this is for what? For deflection control. Now, depth requirement to satisfy deflection criteria is more for HYSD bar, as you can see here, than mild steel. It means HYSD bar, for example, this case of Fe414, where D should be greater than L effective by 28, as opposed to when we have Fe250, where D is greater than L effective by 35, right? So this D for Fe415 is more, which means HYSD produces more deflection than mild steel. Now, when we design a slab, particularly a rectangular slab supported from all four sides, then shorter span is always used for bending moment calculation. That we'll see as we progress. We'll see what is the expression for bending moment, because that first we need to quantify before we start designing. So we will consider the shorter span and then use that to evaluate the bending moment. Now, before we go into the details of that, I'll particularly draw your attention on this clause 23.2.1, where the vertical deflection limit, as it says, may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the values obtained as below. So the first condition says the basic value of span to effective depth ratio for spans up to 10 meter is given here. So if it is a cantilever case, the value is 7, simply supported value is 20, and continuous value is 26. Now the subclause B says for spans above 10 meter, the value in A may be multiplied by span, that is 10 by span in meters, except for cantilever, in which case deflection calculation should be made. So that means if we have span more than 10 meter, then for these two, we can modify with this factor, and we don't need to go for exact structural analysis to find out the deflection. But for cantilever, we have no such options and we have to go for exact estimation of the deflection. So that is fine. Now the subclause C says, depending on the area of the stress of steel for tension reinforcement, the value of A and B shall be modified by multiplying with the modification factor obtained from figure 4, which is shown here. So for that, what we have to do? We have to identify the percentage steel. So as you can see on your x-axis, we have percentage steel here. And then on the y-axis, we have this modification factor that depends on the different types of steel that we use. And then we can apply this modification factor as described in this subclause. Further, it says, depending on the area of compression reinforcement, the value of span to depth ratio be further modified by multiplying with the modification factor obtained from as per figure 5, which is shown here. So, in case of slabs with compression reinforcement, if we have, then further we can adjust. Now, for this slab, the IS code actually provides these two expressions for bending moment. So if I write it, mx, as you can see, is alpha x omega Lx square. Recall Lx is the shorter dimension. So we can also calculate my, which is alpha y times omega times Lx square. Just note, even for my, we use Lx. So we use shorter span to calculate the bending moment. Now, just imagine if we have a slab which is spanning like this over multiple supports, and say we have omega here, then we have to do the structural analysis to find out the sagging moment here and hogging moment there over the support. And depending upon whether it is the outer support or inner support, the value of hogging moment will vary, and we have to find them first before we start designing. But here in the code, we have this dedicated clause here, and with this two formulae, we can actually find out mx and my directly without solving this structure, right? For that, we have a dedicated table 26 where we can get this alpha x and alpha y values depending upon the different types of panel and different types of moment that we can have. I will come to that point later, but for the time being, the point to be noted here, when we design the slab, we don't need to first go for an exact structural analysis, because the applied bending moment along two orthogonal directions, say x and y, are provided by the code itself, where we use shorter direction, the dimension along the shorter direction, that is Lx, to estimate the bending moment. We'll discuss the theory behind this logic shortly, but we get this values of alpha x and alpha y, as you can see here, and then we can directly use those values in our applied moment estimation. Okay. Now, with that background, let us see how we can apply this when we design a slab. For that, what we need basically the bending moment and shear force. Now, as I have already explained, these bending moment and shear force coefficients are already provided, and the clause 22.5 is actually dedicated for this purpose. So it is considered like a continuous beams, and for continuous beams and slabs, which are very common in structural design, so we get this positive and negative bending moment, as you can see in this diagram. So positive in span and then negative over the support. So we can directly find out these values of bending moments that we are going to use in our design. These coefficients can be used if following conditions are satisfied. Member must be uniformly loaded. Then span should be 3 or more. Then difference between longer and shorter span should not be more than 15% of the longer span. Now, when we evaluate these coefficients from the given table, first we need to find out actually the dimensions of the slab, that is Lx and Ly. Remember, these are the effective dimensions. So as you can see here, we have supports over which these slab it spans. So we can see here, this support is actually having some width as also this support. So there is a dedicated clause. So depending upon this type of supports, we need to consider the center line of this, and then that actually will tell us the effective dimension along this direction of between these two supports. So our first task is to find out these dimensions Lx and Ly, and then once we find out this direction, first we evaluate the aspect ratio, and then we decide whether we have a one-way slab or a two-way slab, and then for that we have these coefficients given for these spans as well as over the supports, and then using these coefficients we can directly evaluate the shear force and bending moment. As you can see, we have bending moment here. So if we go for a shear force, also again we have similar coefficients using which we can find out shear force over these supports and its variation as we go from one span to another span. So if we take an example here, we have this bending moment at A. What is the coefficient? You can see here 1 by 12. So we use 1 by 12 WF times L effective square, and That is for fixed support. So if you have not fixed support, as you can see here, then for that we use the coefficient 1 by 10. Similarly, we can also find out bending moment at B, shear force at C, which are marked here. So we have A here, B here, and C here. And you see we have these values of bending moment and shear force that we are going to use. So let us consider the design of a one-way slab and let us do it step by step so that we can identify what are the different calculations that you have to perform before we select the diameter of these main bars and the secondary bars and their spacing. So as you can see on your screen, we have a one-way slab. I have already explained. For that we consider a strip of 1 meter, as you can see here. And the effective depth for this is D. So we'll design this beam of width 1 meter and effective depth D and find out what is the steel requirement and then provide that along this direction. And if it is a two-way slab, obviously we will also consider the orthogonal direction. So the step 1 for this one-way slab design is to assume a suitable value of D for a preliminary design, because we have to first select the depth of the slab. For that we have this L effective by D, and that should be less than this factors times a value that I have already explained. So these are the different factors. We have 4 different factors. K1 that depends on span. Recall these values are given for spans less than 10 meter. Then K2, which corresponds to the percentage of tension reinforcement. Then K3 equal to 1 if it is singly reinforced, and if you have compression reinforcement, then we have to evaluate this K3 from the figure, and K4 is equal to 1 for rectangular slab. Then from this criteria, if we put this here, the only unknown from this equation is D. So we can find out this D, and from that D we can find out what is the total depth of the slab. Over this effective depth, we have to add the diameter of the bar, main rebar, and then clear cover, and we will get this total depth. So that is the first step, because this clause satisfies the deflection criteria. And then we go to the second point where we first calculate effective span. Recall, if we have 2 supports, then center line of the supports will actually tell us the effective span. There are other conditions also in the clause, but for the time being, if we consider the center line of the support, that will give us the effective span length. So our task is to find out Lx and Ly. Once we do that, in step 3, we need to calculate the applied bending moment coming from different load combinations. So we start with dead load and then use bending moment coefficients to find out what is the value of the applied bending moment. Recall, mx is equal to alpha x omega times Lx square. Similarly, we can also find out my, right? So for one-way slab, we have dominant bending along one direction, obviously the shorter direction. So we find out mx, and then in step 4, we calculate small d required for a balanced section, right? And if you recall from the beam design, mu limit is q bd square. So this expression is known to us. So for a balanced section, we can calculate the capacity of the section or the moment of resistance of the section. From this, we can calculate the D, and that D should be less than the D assumed in step 1. Otherwise, we have to actually go back and repeat the steps from 2 to 4. Then once we satisfy this criteria, we have already satisfied the deflection control and now the applied bending moment. Then in step 5, our task is to find out AST, and For that, again, this expression is known to us. We have already considered B as 1 meter. So in this expression, if we put 1 meter width of the beam, we can calculate AST required. Then if you recall the beam design, we need to find out the AST minimum because the minimum amount of steel we have to provide. And if this AST provided is more than AST minimum, then we can carry on with this value, or otherwise we have to provide the minimum reinforcement. Then finally, in the step 7, we have to provide distribution of this reinforcement. Right. So these are the fundamental steps that we have to follow. We'll take some example and we'll see how we can evaluate the amount of steel we require and how we distribute them along the span of the slab to take care of the bending in the dominant direction. Now, before we go into the details of this example, let us quickly see the different distribution of reinforcement. So, we have this span which is continuous. So, we have supports here and support there. And if you recall the bending moment diagram for this case, we have 0 here, then maximum sagging here at the middle of the span, and then over the support we have hogging moment, right? Accordingly, we have to provide the stills. So you can see here we have these stills for sagging moment at the middle of the span. Then as we go towards the end, we have at this end we have 0 bending moment here, but again we have to provide a minimum amount of steel there over the support. As you can see here, over this support we have this AST. Negative means the hogging moment and positive means the sagging moment. Now this rebars, for example, the rebars at the middle, as we go towards this end, we can curtail it up to a certain point. And in the previous lecture, we have discussed in detail what should be the region for curtailment, right? Now, in case of slab, this point of curtailment, as mentioned here, is 0.15 L. And for the support, if it is discontinuous here, then from the face of this support, this reinforcement will extend up to 0.1 L. Now for intermediate support, again we design this value of AST minus. Then as we go towards the middle of the span, obviously the top surface is in compression. So we have this steel at the bottom for that. So we can reduce the bars after 0.15 L from this face. So from this face, the first curtailment is where we have this point. Then we extend half of the bars, as you can see here, up to another 0.15 L. And obviously here there is no requirement of steel. Now we have already explained for the edge support, from the face of the support, we have to have this point where we can curtail the main rebars at the bottom. And this distance from the center line is 0.15 L. So we know the width of the support. So from the edge of the support, we can also calculate if this length is required. Now the point to be noted here for intermediate support, from the center line, it extends on the either side up to 0.25 L. So this point where we can curtail the main reinforcement for sagging moment once we come closer to the support, and this is 0.15 L. Now just notice some of these bars are continued over this support as we go from this span to this span. So the theoretical deflection is what we have here for this hinge support. But the practical deflection is what you can see here, and this is because of the reason we have to actually extend this region. So we have to have rebars at the top, and then we also curtail bottom reinforcement at this point. So that is the difference between theoretical and practical deformation of the slab over this support, right? Okay. So now take an example. So as you can see here, we have to design the continuous slab with equal spans. As you can see, it is spanning over these supports, right? So support width is given, it is 200 millimeter. Then for this slab, we have a floor finish of 65 millimeter thick. So unit weight of the floor finish is given, that is 22 kilonewton per meter cube. And then live load, which is uniformly distributed over the slab, is given as 6 kilonewton per meter square. So we have a mild exposure, and for this mild exposure, the concrete is M20 and Fe415 steel. So let us first find out the D effective from the deflection control satisfying this clause. So for that, we have in the step 1 is L effective by D should be less than equal to these factors times the value. So for these spans, the center line between the two supports defines the effective span length, which is 4 plus half the width times twice, so it is 0.2 divided by D should be less than this K1, K2, K3, K4 times the value. So this comes from the Codal reference that we have already discussed, and from this relation what we get is D should be more than 146.08. So anything more than this D is sufficient, so we can provide say D 150 or for that matter any other value. So let us provide D as 150. Let us try with that. So along the dominant direction, this is the D. So this is our main bar, and the center line of this main bar from this top surface is small d, which we assume as 150. Now what should be the capital D, that is the total depth? It is a small d plus allowance for reinforcement. So we have to have this half the diameter here. That is the allowance for reinforcement. As of now, we do not know the diameter of the reinforcement, so we will assume something and then we'll check whether that assumption is okay or not at the end of the design. If not, we have to readjust. Then we have to add the clear cover. Remember, we have mild exposure. For that, clear cover is 20 millimeter. So the total depth is 150. That is the small d that we provide along the predominant direction, plus we add 10, which is assumed for the time being, which is the half the diameter of the bar. That means we propose 25 bar along the main direction. Then for mild exposure, we have 20 millimeter. Effectively, total capital D is 180 millimeter. So now we have an idea of the total depth of the slab. Then we come to step 2, where we evaluate the effective span, assuming that the slab is simply supported for the time being. So L effective is less than minimum of these two conditions, LC plus D. Recall LC is 4 plus D, what we assume here as 150, so it is 0.15. So 4.15, or the second condition is B1 by 2 plus LC plus B2 by 2, which is 4.2 meter. Remember, B1 and B2 are the width. So here it is B1 and here it is B2. Both of them are 200 millimeter. So L effective what we get is 4.15. Then once we evaluate L effective, we come to step 3, where first we calculate the load applied. So we have self weight of the slab. Remember the total depth is 180 millimeter, and that's why we have 0.18 times 1 times 25 kilonewton per meter cube, that is given in IS 456. That is the density of the reinforced cement concrete. So using that, what we get is omega is 4.5 kilonewton per meter. Now on top of this self weight, we have floor finish. Remember the thickness of the floor finish was given, that was 65 millimeter. And then for floor finish, we know the density and we can calculate the corresponding value of load per meter run. So for this problem, we have fixed loads coming from the dead load and the floor finish. And then we also have live load. So we can find out the live load per meter run, which is 6 kilonewton per meter. So now we have finalized the load acting on the slab, and then what we go, first we apply the appropriate load factor. So dead load factor, if you recall, it is 1.5. So accordingly, we find out the factored value of the fixed load. Similarly, we find out factored value of the live load. And then based on the support conditions, we can find out bending moment positive, which is here. That comes from this coefficient that we directly get from the Codal provisions. So positive bending moment, what we have is 28.26 kilonewton meter, which is sagging. Similarly, we can also calculate the negative bending moment, which is shown here, and that is 32.53 kilonewton meter, which is hogging. So once we evaluate this two bending moment, then our remaining task is to design the sectional capacity so that it can withstand this applied bending moment. For that, we go to step 4. Then for this Fe415, that is the steel that we use, we find out what is the sectional capacity or the moment of resistance for the balance section. And for that, the formula, if you recall, is QBD square. So for this Fe415 steel, ultimately it turns out as 0.138 times FCK BD square, right? Okay, so now what we do, we equate this value of balance moment with the applied moment. Then what we get is the D required, and obviously this D required is less than the amount of D provided, and hence this design is okay. So we provide more depth as compared to what is required. Now that means if we provide more depth in step 5, we conclude that it is a under reinforced section, and for that under reinforced section we can easily evaluate AST plus, right? Now in this expression, recall, we consider a 1 meter wide, and hence this B is 1000 millimeter here, as you can see. And for this 1 meter wide beam, we have AST requirement of 566.46 millimeter square. Following the same steps, we can also find out AST negative, and which is 661.48 millimeter square, right? Now here, because we have a first calculation, an exact calculation will be where we use a different value of D, because if we have, say, this is the cross section of the 1 meter wide slab that we are designing here. So we have main rebars running like this, and the secondary reinforcement running like this. Okay, so for main rebars, this is the depth. So if the need be, we can actually modify this, but for the time being, we use the same value, which is 150, right? So whether it is mid-span or over the support, we have same. As we go in the 2A design, we'll see we'll use a different value of D, because for the other bars, it is somewhere here. Now for this problem, AST negative is 661.48 millimeter square. So first what we have to do, we have to check the minimum steel requirement, that is AST minimum, which is in our case 0.12%, because we use Fe 415. So minimum requirement is 216 millimeter square, and obviously we provide more than that, and hence it is okay. Now, from this estimation, what we see that AST positive and AST negative, they are not very significantly different. So for this problem, we can actually provide the same amount of steel, obviously the higher value of the steel in both the directions. So for this positive as for this negative case. Why? Because this will offer a easy construction, because at site, at the mid-span, we have this positive value, and over this support, we have this negative value. So if we have different amounts of steel, so we have to provide different steels there. In case if we decide that we go for the same, so then construction becomes easier. Now, assuming phi to be 10 millimeter, recall at the very beginning, we considered 20 phi dia bar, but here, ultimately, let us start with 10 millimeter bar. So then the spacing of this bar, as you can see here, is 118.73 millimeter. So over a width of 1 meter, we find out the number of bars from this relation. So we have AST negative that we provide, which is 661.48, divided by the cross-sectional area of a 10 millimeter bar, as you can see here. So this is the number of bar, and when we divide the width B here divided by the number of bars, we get the spacing. So we provide 10 phi bar at the rate of 100 millimeter center to center, because we have here as 118, and if you recall, we always try to provide at the rate of 25 millimeter, nearest integer of 25 millimeter. So instead of say 115, we prefer to have 100, because this is roughly about 4 inch. 1 inch is 25 millimeter. So that's the reason at site it is provided like this, either 100 or 125 or 150, like this. We cannot provide 125 here, which is actually more than the spacing evaluated from this expression, and therefore we provide 100 millimeter center to center. Then we have to provide distribution steel, secondary steels, if you recall. So for that, again, our minimum amount of steel is 216 millimeter square. So for that secondary steel or distribution steel, we provide 8 phi bar, and again we find out the spacing, which is 232.71. So let us propose 8 phi bar at the rate of 200 millimeter center to center. In fact, we could provide bars at the rate of 225 millimeter center to center, but let us propose 8 phi at the rate 200 millimeter center to center, which is obviously better than this value, because we have closer bars and we have more number of bars. Now let us see the different rebars in the detailing, right? So as you can see, we have main bars here. Recall it was 10 phi at the rate 100 center to center, so that you can see. Then we have secondary distribution reinforcement, that is 8 phi at the rate 200 center to center in the orthogonal directions. Then over this support, we have this from AST, recall AST negative, and we have actually provided AST negative in AST positive also. And that's the reason you can see here we have the same diameter and spacing over the support and in the midspan. Then for these bars, we actually have a nice arrangement. So half this bar actually is taken here and it is bent and kept over this support. See, it goes there. And then we extend some of the bars up to 0.15 L that I have already explained. Now over this support, which is the extreme end, here also we have to provide the support steel at the top, and which is, as you can see, 10.5. Half of the bars we take at the top, and that's why we have 200 center to center, which is coming from this 100 center to center. So half of the bar we actually take it to the top over this support. And if we see the plan of reinforcement, you can see here that is the arrangement. So half of the bar extends beyond this 0.15 L, while half of the bar is curtailed at this point. So that is the arrangement of the bar we actually provide to the site engineers in the form of structural drawings. So we start with the basic dimensions, then satisfy all the code clause, and then at the end of this we have these kind of structural drawings ready for the construction engineers. So construction engineers will follow all these rebar proposals, and accordingly they will first prepare the rebar setup, and then they place that within the formwork with sufficient amount of clear cover, which is provided here, and then pour concrete within the formwork, cure it for 28 days, and then remove the shutter to get this slab constructed. Right. So that is the step-by-step design procedure for a slab. So with that, let us close here. Please go through all these steps, and in the next class, we will see how we can design a two-way slab. If you have any query, do let us know. We will clear your doubts. Right. Thank you very much.